That's exactly what Michael Faraday and John Henry. From my previous videos about Ampere's law and Biot-Savart law, we saw that current induces a magnetic field. It is logical to conclude that the converse should also be true, that magnetic field should induce current. That's exactly what Michael Faraday and Joseph Henry thought. And after independently performing a series of experiments, they found that magnetic fields can induce electric current in a closed loop only if the magnetic field is changing with respect to time. This discovery led to what is now known as Faraday's law of induction, which says that if I have a coil of wire located in a magnetic field, then the voltage induced across that wire, called the electromotive force or EMF, is equal to negative N, which is the number of turns of wire, multiplied by the time rate of change of the magnetic flux phi. In other words, I'm taking the negative of the number of turns multiplied by the derivative of the flux. We can find the magnetic flux by taking the surface integral of the magnetic flux density B over the surface that is enclosed by the loop. If you were really curious, you would say, why is this important? Well, thanks for asking. One really great application of Faraday's law of induction is electric motors, which we experience on a daily basis. Another great application is just using the fundamental principle to measure magnetic field fluctuations. In my research work, I have worked with powered magnets. These magnets possess much higher field strengths than traditional superconducting magnets. Increased field strength has a ton of great benefits for performing nuclear magnetic resonance experiments. Unfortunately, powered magnets suffer from a magnetic field that changes over time. We call this change magnetic field fluctuations. It turns out that this is problematic for performing NMR measurements. To deal with the change in magnetic field, we designed a feedback control system to compensate for the magnetic field fluctuations. To perform feedback control, we needed a measurement of those field fluctuations. So, we put a coil of wire inside the magnet and measured the voltage induced across that coil. The voltage induced was proportional to the derivative of the field fluctuations, and this gave us a measurement we could work with. So, those are some practical applications of Faraday's law of induction. Several things can cause change in magnetic field. The first case is where there is a stationary loop in a time-varying magnetic field, just like the real-world example I gave. In this case, the induced voltage is called the transformer EMF, VEMF transformer. The second case is where I have a magnetic field that is constant, but I have a loop that moves. And it moves in such a way that the area relative to the normal component of the magnetic field changes over time. In this case, the voltage induced is called the motional EMF, VEMF motional. Finally, we have the combination of the two cases. In this case, the total induced voltage is equal to the sum of the previous two cases. Hopefully this video has provided you a reasonable introduction to Faraday's law. In a classical electromagnetics course, you will more deeply explore each of the possible cases of Faraday's law. That's all for now. We'll see you around.